We have Dr. Aenor Sawyer here with us, and I'll introduce her in a second. But also just to introduce her to us, we are women in aerospace medicine, and also in case this is your first meeting, welcome. And we're basically an offshoot of AMSR, which is the Aerospace Medical Students and Residents Organization. So we are a bunch of doctors or student doctors in various stages of our training. And especially we're here to support women and minorities in this field. So we've had a couple of great events already, and we're very excited to have another one. This is just a quick rundown of who we are. So we basically have Nelly, myself, Shilpi, Eleanor, and Shayna. And we're all in various stages of our training, and we've been kind of working behind the scenes, trying to do some mentor pairing, and organizing talks and getting information out to you all. So if you have any questions about what you see or hear today, or any ideas, please feel free to get in touch with any of us. We are here to help you and help each other make this a really cool and informative session. All right, so today we have Dr. Aenor Sawyer, and we also have, hopefully coming up this weekend, we're releasing our new website. And we have this beautiful new logo, if you take a look at the left. And we have some upcoming events as well. We had mentioned a few of them before, and we have now Dr. Cheryl Lowry, who's a flight surgeon, hopefully coming up in December. We'll give you guys the date as soon as we have it. And then in January, we have Dottie Metcalf-Lindenberger, who's an astronaut. So that should be a really cool talk as well. But without further ado, let's introduce our wonderful speaker, Dr. Aenor Sawyer. Dr. Aenor Sawyer is trained classically in orthopedic surgery, and she has over 2 decades of health innovation and technology experience, as well as some really interesting experience with extreme and remote environments. She has many accomplishments, but some of them include the fact that she's the Chief Health Innovation Officer at TRISH, which we heard all about last time, which is just the NASA-funded Translational Research Institute for Space Health. And beyond that, she's also the founder and director of the UCSF Space Health Innovation Center. So hopefully we'll hear a little bit about that as well. And she's joining us today to discuss some of the space health technology and her path, hopefully, as an orthopedic surgeon and innovator. So without further ado, let's welcome Dr. Aenor Sawyer. So I'll turn it over to you, Dr. Sawyer.
All right, thank you so much for this opportunity. And I know everyone is quite distracted right now, and I completely have no hard feelings if you also have to look over at your TV monitor once in a while, especially for those of us in the US, although I hear all eyes around the world are on our election right now. But so no hard feelings if I see you glance away. I'm just really thrilled to be here, and I want to thank WAM and the organizers for inviting me. So let me switch over and share my screen. This is always a high wire act. Make sure this works, and I'll go to presentation mode, and we should be all good. Thanks for the head nods. All right, so I'm going to have a presentation today that's fairly a broad brush stroke across what I consider a need for a space health continuum, and it's going to be informed by terrestrial healthcare. But as I always say, it's a mutually beneficial experience to work both in earthly healthcare and space healthcare. They each inform the other, and it's a real great opportunity for us to borrow from both and use both to transition and expand and transform each entity. Those are concepts I know you're well aware of, and I'm going to be speaking on things that you may already know about, but I just want to frame them in a way that you might not have thought about. So as the Chief Health Innovation Officer at TRISH, thank you for saying the whole name so I don't have to. My role is to understand human health risks in space, particularly deep space, and to source innovative solutions and look for what I call space relevant, space adaptable, and potentially space feasible technologies. And what I mean by that is, could these technologies possibly be compatible with the tenets of space, including mass, power, volume, and the radiation dangers, et cetera. So all those tenets, and then also be multi-user capable. And I do this through a platform I call TechView, where I present to the TRISH leadership team and to some NASA interested groups. But I do a long curation process, constantly landscaping technologies, which I do for healthcare anyway, for our healthcare system. But I'm also then down selecting to ones that meet these criteria: space relevant, space adaptable, space feasible. In addition, in TRISH, we're facilitating research development and space specific validation, which means we actually fund projects and fund groups, and we also fund trainees. So I'll tell you a little bit more about at the end, but I know you got some of that from Dr. Donneville last time. So our role, TRISH plus NASA, is we're to provide astronauts with knowledge and technology to enable them to maintain their optimal physical and behavioral health, and to provide them with capabilities for self-health and medical care in a model I've nicknamed augmented to autonomous, or A to A, to mitigate themselves from damage from space radiation and other environmental hazards, ultimately overall optimizing crew health and safety, and in addition, performance. So to do this, we're going to need to have capabilities that will allow us to pick up on early deflections from baseline health, and also then to enable informed choices to right those conditions. And we've got to do this in a way that is very adaptive and very personalized. So these are the main concepts about what we're talking about today. And then again, in context of the space environment, which I won't repeat because I know you have most of these memorized already. But when you think about the environment, these are actual variables in the environment. They will change, as will the human. And this is a concept we need to get clear on, is that our bodies will be changing over time as well. And we've only measured out mostly to 6 months, but beyond 6 months, there are some changes that are expected to continue, such as bone and muscle loss. Others may reach a homeostasis and stay there, such as the fluid shifts and adaptations with the early diuresis, et cetera. So those are conditions that we need to know a whole lot more about, but we've not been able to do significant integrated monitoring of all of these systems, and to do that across time longer than 6 months. We're doing some small ends in the 1-year mission that's coming up, but we're going to learn more over longer duration. So again, as you know, the ISS is where we are now. We have 20 years of experience. Happy birthday, ISS. And we also have the ability to keep using the ISS as an analog as we move out further towards Mars, starting with the cislunar missions. But each of these levels provides us different variables and challenges to work with. So it's really important we understand what we're designing our health and medical capabilities for. And again, we're going to be using the ISS, which is basically fairly well contained in terms of health and medical. They could be doing a lot more monitoring and a lot more closed loop processes, and that's what we're going to be striving for there. But they're basically a telemedicine model. We have synchronous communication back to base. Even if we take an image, we can push it back and get it analyzed and then information back, or real-time guidance with any procedure we need, et cetera, or decision-making. That's going to change a lot as we move further out and on longer missions. As you know, the low Earth orbit is hundreds of miles away, but when we're up around the moon, it's hundreds of thousands of miles away. And when we get out to Mars, it's hundreds of millions of miles away, which presents new challenges. The most important challenges to think about are that they're at Mars, delayed communication. So asynchronous communication basically is what we have to plan for, with intermittent and timed and planned pushes of information, but not anticipating real-time guidance. Also, there are very limited supplies that will be taken and no opportunity for resupply. So how do we create sustainability models? No immediate return, so we can't put deorbit at the bottom of our medical acuity checklist. There won't be an opportunity to take an astronaut off the spacecraft and get them back to a higher level of care on Earth. And there will be more radiation and other types of radiation than we're exposed to at this time, including galactic, cosmic, and very confined space over long duration missions. So we've got to work hard on this A to A health and medical management model. For me, it goes back to what I've been working on Earth for the last 20 years, which is getting to precision health continuum. What I mean by that is it certainly should be more individualized than we do now. We base a lot of our decision making in healthcare, and I'm still in healthcare. I'm the director of the Skeletal Health Service at UCSF and still seeing patients. But in that, a lot of our information comes from population-based algorithms. And we have to figure out how we can continuously factor more of that individual's data into the equation when we're trying to help them, guide them on treatment paths. But also our bodies move, our physical bodies move across a spectrum of wellness to illness and back again, but our devices and our data don't move with us. An example is if you're running the Beta Breakers, which is a race out here on the West Coast, and you've got all your activity data you've been collecting over the last 6 months and training for it, but you suddenly drop and collapse and have a syncopal episode or an MI type episode. The ambulance will come, they'll put their own measuring device on you. When they move to the hospital, they'll take that device off, they'll take the data strip they printed and tape it on the back of the clipboard in the ER. They'll hand that over. You may or may not still have your activity monitor on you, but the ER will put their own monitor on you and they'll ignore all the advice, all the information coming before that, which could be highly predictive or even diagnostic as to why you might have had that syncopal episode. And they'll start with their own data and their own devices. So this is why I strive really hard on the concept of a precision health continuum. Part of it came out of my experience in the last 15 years covering ocean rowers, who I say come back a cross between a prisoner of war and an astronaut. They're out at sea in these 6 by 23 foot boats. They're unsupported and they're out at sea for months. They take everything with them that they're going to have, or they'll have to figure out how to do without it or make it. And also their health and medical system is much like we're going to be building for deep space. So I work a lot on remote medical management. I do have the opportunity for satellite communication, but again, that's very intermittent. So we have to make these as self-contained as possible. So a lot of that continuum, the health continuum, is also modeled after remote care that I've been giving. And I'm not going to go through all the changes to human in space here, but I do want you to keep in mind that all of these systems are integrated in one body, and we oftentimes silo them. We silo the way we look at them. We don't think about how integration of these systems could either benefit or compound the negative aspects of what we're seeing. And so I think that just wanted to put that up there so we see a lot of things on one slide, but I'm not going to go into them in detail. But what I'm pointing out is our monitoring systems that we're developing should no longer be point solutions. We shouldn't be figuring out how we're going to just monitor that. You have to get narrow and focused to do a good job of assessing bone and muscle loss or neurovestibular changes, but you've got to constantly be thinking about how does that system integrate with another, and how would my data collection and my data utilization integrate with the other to create a whole picture. And beyond that, we've got to integrate that individual's data with the team's data, and then integrate that with the environment's data. So this is the concept that we're getting at, and you'll hear certain phrases over and over. And some are ones that I use. You might not hear other places, but there's a similar concept with a different name, perhaps somewhere else. But a lot of this is really to enable distributed but not diluted healthcare. That's a concept that I keep striving for as we work in low resource settings. And this is going to be optimized by the technologies that are evolving at such a rapid pace. And I think you've seen great examples of this in the COVID era, where we've been forced into non-contact or contactless healthcare and medical management, and individuals doing more and more to optimize their own health. So we need to keep those lessons going forward, and we need to figure out which of them were valuable and which of them were fraught with problems, and how do we right those problems. But it will help us ultimately get away from siloed care and this episodic crisis management, and also these incomplete recoveries where we're forced to get people out of the hospital early, but then they go out with no net, as we say from my old circus days. They go out without any monitoring, and we have very little visibility, even though we're still emotionally responsible for them and in some ways fiscally responsible for the outcome of their care. We don't have good visibility on what's happening with them, and we usually can't get a handle on that and do anything about it until they show up at the ER in a crisis again. All of this concept is to get to what I call informed health, which is getting the right information at the right moment to make the right choice. And that gets us to an optimal outcome. And it's the way we live our lives right now. We hold the phone, which is a computer, in the palm of our hands, and we ask what we need to know, and we expect the answer right then, and that optimizes our choice. whether it's getting across town or booking a restaurant for dinner. So that's the type of standard we need to start holding healthcare to. So this precision health continuum will really depend on understanding and characterizing well the optimal baseline function, or the baseline function that the patient meets you at. I'm thinking more in terms of the astronaut. Hopefully we've got in the pre-mission period, we've selected well and we've got them trained well and optimized for their mission. And then from that, we need to be able to pick up on critical points of perturbations or deflections from baseline, and then analyze those, get information back, or pick up on when they've gone into a clinical pathway, diagnose it quickly and treat it quickly, get them back around to recovery. We're doing this a lot in healthcare now. I'm sure each of you are familiar with programs where we're doing home-based hypertension management, where we're actually giving algorithmic driven capabilities for patients to make certain adjustments in their own medications based on their monitoring and the decision support provided them, with a backup plan of contacting us for things that are out of range. But the point is, more and more of healthcare for chronic disease is moving towards this. And I think it's something that we can learn a lot from as we look forward into how are we going to create optimal health and medical management in deep space. So this is just an example. There are many of these diagrams, but here's the human with sensors described well, getting feedback to themselves, getting feedback to maybe their trainer, getting feedback if necessary, if it gets escalated on the red, yellow, green scale over to a physician or a clinical provider, and if necessary, intersection with the healthcare system. The information that is being given here and giving guidance should integrate with baseline medical history and medical data. But ultimately, if you end up in this illness zone again, as you transition back out of it, your data and your devices should all remain integrated because you are one body. And we have not done this yet in healthcare, but we're working more and more towards that direction. We have small examples of it, but it's certainly not standard of care yet. And we're hoping that the lessons learned in COVID aren't just one-offs and they aren't just in times of disaster, but that we actually integrate remote care as a part of the tapestry of healthcare that is deeply connected. So the precision health continuum model really depends on a couple of concepts. One is this is person-generated data, PGD, in the context of environment-generated data. And it all fits under, these concepts around real world evidence that you're hearing about. And the ONC has written really nice descriptions of how to use data from the real world. But it's really understanding what's happening to the person in the real world of their life. So what I call life flow, and how the environment around them is influencing them and they're responding to it. This requires not just qualitative, but also quantitative data. We learned a lot about symptom checkers in the era at the very beginning when we're trying to find out who might be infectious or infected and what patterns of transmission were happening, but we were still lagging when it came to quantitative information. The one thing people were adding really was temperature, and it's still highly debated as to how predictive that is of whether a person is infected or infectious, but it was the one thing we could measure. So we're adding more and more capabilities in. If you wanted to, you could sign up for the DETECT study, which Scripps Institute was highly involved in, leveraging symptom checkers, but your activity monitor. They did a good job of linking in Fitbit, I think Apple Watch and Garmin data on activity, heart rate, et cetera, and putting those into algorithms that were helping with predictive modeling. And that's actually been based on a Lancet article where they were able to predict outbreaks of infectious disease by doing that same thing, using devices people are already wearing and integrating that information and giving feedback. So that's where some of that, the concepts around that came from for the DETECT. And there are many platforms like that. That's just an example. By the way, things I mentioned in this as specific examples, they're illustrations. I have no conflict of interest with any company I'm presenting today or with any specific research group. I'm just trying to put forward things that I think have distilled up to the top for me. So what I've called all this is a need to focus on the metadata, not the metadata. I call it metadata because it's the data that matters. So rather than taking approach of let's integrate all kinds of sensors and disparate data streams, let's start at the other end and figure out what the question is. What's the so what factor we want to get out of this continuum? And what are those use cases and what data streams do we need that feed into something that will be predictive or diagnostic perhaps? So the data needs to be relevant, and it needs to be relevant to the individual, but also to their setting and to the question being asked. So is it critical in nature? Is it consequential or drives key decision-making points? And how can it fit in and contribute and actually amplify data coming from other data streams? So we have a multi-parametric sensing suite that has hybrid vigor by combining, and you get more than the sum of the parts. So this is just an example of how we're using this concept in the ICU, and this is Hopkins and UCSF combined, building an eMERGE platform. And we really went after the data streams in the ICU, which is the most highly monitored setting you could be in if you're a patient. But the problem is none of those systems were connecting. The anesthesia monitor, the physiologic monitor did not integrate with the EMR, did not integrate with the lab data or the imaging data or the nurse's assessment for that amount, or even the patient's symptoms. All of that only came together, as you know, in your medical training, only came together in the intern's head for 10 minutes when they had to present it all on rounds. But other than that, there wasn't an integration of all those things until these types of platforms started being built. And now we're actually able to detect deflections from different systems and integrate that information. And we've been able to decrease the highest causes of morbidity in the ICU, and decrease length of stay, and decrease overall length of hospital stay as well. So this is very important. Some of the causes, as you know, are pneumonia, line sepsis, et cetera, overfluid, delirium. So that's just an example in the ICU. This is an example that started as a research tool that became useful in the clinical setting finally. Most MS is relapsing, remitting, very challenging disease. And it's very hard to tell people anything about what they'll be like in 3 years or 4 years, or what treatment they might respond to, before we could integrate all this data. So we had collections of data at UCSF in large data sets, from imaging to genomic information, to pharmacologic response to functional scores, but it only came together in research meetings and about 4 years later in a publication. None of this was accessible to the clinician or the person who were trying to make decisions for themselves. So now we're presenting it in these dashboards, audience-specific dashboards, so people could look at them almost like a height and weight curve for pediatrics. You could pull up different parameters, you could pull up define different peer groups around that patient based on the different parameters. And it's observational analytics, but moving towards predictive and hopefully prescriptive analytics in the end. This is one tool being used out in the community. This is Omada Health. I use this a lot for prehab, preparing patients, optimizing their general health for surgery or helping them avoid surgery. And this basically is a platform that combines some key features. It combined not just monitoring capabilities. So here's activity gets fed in through your phone. Your scale is sent to you, it's digitized, it's pre-synced, you don't have to mess with it. And then you add in nutritional factors that you're recording for yourself, and you add exercise education, stress education, sleep tracking, combining all of these things, but adding behavioral science capabilities that we know about, peer support, one-on-one coaching, frequent reminders, etc. So this is a tool that's highly validated, has been shown well to keep people who are pre-diabetic from becoming diabetic, to help type 2 diabetics manage and avoid episodic type management, to decrease risks of health in diabetes, stroke, and heart disease. There are several platforms out there. I have no affiliation. I use this a lot, and I found it to be one of those tools that helps people stay engaged and has long-term results. Those are the types of disparate data stream integration with feedback that we're going to be striving for our astronauts. I'll skip this over, but it's just to show that these types of multi-data stream platforms for remote medical management are becoming core to all types of research. So distributed clinical trials, the ones that use distributed clinical trial concepts kept going during COVID, but a lot of research trials where they're still making the patient or the client come to the facility, a lot of that research stopped, and it's been devastating through the COVID era. So looking more about how you can leverage these in research as well. And the military is on this continuum idea. So they've got a model that they're working with and leveraging lots of technologies, but the core idea is data, receiving and transmitting data through a continuum of care. So if if a soldier has an injury, they go to the aid station. The first place they get is immediate resuscitation on the battlefield. Then they get to a station. Then they get to theater or hospital. Then they get medevaced. they move on around to higher levels of care, and then ultimately trying to get them back into a recovery and readiness program so they can get back out and function again. But if they end up in the veteran system, all of that data should flow. It should flow all the way, to be honest, from boot camp, so that we know if they're ready or not. And between combat missions, are they ready to get back out on the field, et cetera. So many of these concepts are being pulled together in the military health continuum of care. So let's talk about more specifically around space. And you'd think I'd be going forward and more futuristic, but I want to step back in history a bit to Hippocrates. And I think it's interesting because, it's the foundation of much of what we do in medicine, but also I had no idea there was actually a crater on the moon named after Hippocrates. And so that was fascinating to me. But the reason I call him forward into this moment is because there's this phrase that I think is so profound. It's far more important to know what person the disease has than what disease the person has. And this is what's driving us more and more in precision medicine. And if you look at the astronauts that go up, they're small n's. So much of the information that drives us in terms of guidance around them is really population based, where we try to match a demographic that's, quote, astronaut-like. And some comes from the small n's and the small data collection we have from actual astronaut experience. And so what we think about, though, is how could we possibly get more information from each individual that will inform the whole, but will also inform how do we manage that individual much better, rather than the large data sets that we're drawing inferences from. And you can see there are quite a few differences here. One you see right away is, here's a woman who's going to have very different responses in some physiologic parameters than men will have. And and different ethnicities, different gene pools, different aspects of development. The first 20 years of life are highly influential on reaching peak bone mass or not. So there are many things that make understanding each person really critical when we talk about optimizing their health and medical management. And in addition, trying to predict what types of conditions we might need to prepare for with each individual. So again, the continuum requires that it's individualized, that we're able to pick up on the individual and the environment, that we can detect subtle changes and understand which ones are meaningful, what are the ranges which should generate concern, and create actionable insights. And overall, the whole system has to be adaptive and learning. What that means is the algorithms have to be able to be refreshed as that human changes over time, or the environment changes as well. This is just a graphic example of what I mean. If you start up here in the optimal state of wellness or functional well-being, can we possibly pick up on early deflections that might be critical or might be important? If we pick up on a deflection, a person their reaction time has slowed down to a level that we think we should offer an intervention, offer a suggestion of more rest time, et cetera, or different sleep hygiene, or even with hydration, or picking up on other parameters around nutrition, et cetera. So this idea of early deflection, detection of that, giving an actionable insight and correcting it before they deteriorate down a clinical path. If they get into a clinical path, or that's the first moment we recognize there's something wrong, then what can give us rapid diagnostics, clinical decision support, and then a monitoring of that intervention to make sure it's right or could be corrected, and then a restoration back up to this state of wellness that was previous, or a new state of wellness, and adapt our program to that. So an example is hydration, looking at hydration or low volume, or even to the extent of dehydration. And if we pick up on it here, we can write that. We can give them instructions on how to maintain better hydration, how to correct acutely and chronically over time. Or if we don't pick up on it, we'll see a higher risk of stones, a higher risk of infection, which we do see in space, and probably renal insufficiency, if we were measuring, is happening a lot up there. And we're not measuring it, but that chance of renal insufficiency is great, and it can transfer if we keep going and we don't actually pick up on these things into renal failure, which can be reversible depending on the stage of it, but it also can be irreversible. This is a huge problem for me in monitoring and maintaining optimal health for rowers. They become very dehydrated for similar reasons that astronauts do, and they have a hard time. We have a very hard time quantifying it and picking up on it early. We have had rowers go into renal failure, and some were irreversible, sadly. So this is a problem that's a parallel between rowers and space, but it's also an example of an astronaut, whether we need to be able to have this kind of a continuous monitoring or an awareness, whether they're exercising, whether they're at rest doing their tasks in space, or even outside when they're doing an EVA. We need this level of awareness for them, and that's going to require intense data and device capabilities. But basically, it comes down to these concepts. We need awareness, we need analysis, so that's the computational side of it, and we need action. We need to give directions. We need to leverage that information all in a closed loop fashion. And this is where we're driving towards when we build towards the Mars model. In NASA, they're calling the same thing that I call awareness, analysis, action. They're calling it, I think they're calling it detecting, deciding, and doing. I just heard this from the medical data architecture team in a meeting yesterday. So very similar. But the other pieces are we need this data to be accessible. So we've got to figure out which data can we get access to. If we know in a terrestrial model in the ICU, that information is incredibly important to a decision tree, can we get access to that data remotely? Are we going to have that capability? And that's what we're striving for on individual sensing solutions. And then can the processes be automated as much as possible? We find that most apps that require you to do a lot of data entry manually, they fail. You lose early on your clientele, and the system has to be learning and responsive. I'm going to step back for 1 second on this concept of what keeps engagement, because we have a lot of studies showing that by 6 months, many of the health wearables or health apps are abandoned within 6 months, 50% of them. So I started looking at that a lot. And what I've learned over the years of using these and trying to build systems is I've come up with something I call the value to nuisance ratio. If we're not giving enough value, and value that means something to that user or that stakeholder, whether it's the crew medical officer overseeing the whole crew, or it's the individual, or it's mission control, if we're not giving that stakeholder the right value, then we're not going to be able to overcome the nuisance factor. And everything we introduce will have a nuisance factor, whether it's battery life, or whether it's discomfort, or whether it's a bulky wristband that you have to accommodate. So we've got to keep the value above the nuisance with any of these things that we're introducing. Some of these themes I've already talked about. These are what I call the PRD, or the product requirement definition. It's a bit of an engineering innovation term that we use to build what's called the health sense matrix. That's what powers the whole continuum. And so the themes are really some we've already talked about. We've got to maintain, not abandon, security and privacy, and then redundancies and capabilities you hear a lot about in space, role-specific interfaces and feedback, obviously getting to autonomous. The components of that will be sensors that are in multiple categories. So this health sensing matrix is really going to be a tapestry of a suite of sensors, from contact sensors, which includes wearables, adhesibles, even implantables, and they need to be as low powered or even self-powered. We have implantable self-powered sensors that are being developed now. It can be a combination with non-contact sensors, which there will be, and we have some examples of that already underway, optical, audible, vibration, radio frequency, even thermal detection. And we're using these even to understand how patients are doing in their room, especially in the time of COVID, where we're trying to minimize people going in and out of the room. We were leveraging all types of sensors that would give us patient information without people going in and out of the room, changing PPE and increasing contamination. And then environmental sensors we've talked about already, but as you know, in space, we're going to need to have a continuous flow of information about that astronaut's environment. And point of care diagnostics have to feed into this health sensing matrix, not be a separate platform from it, which that includes their medical history, their labs, their imaging, et cetera. And then integrating all of these data streams, feeding them into a highly intelligent computational layer with what's called edge analytics, meaning those processes can be determined right at the site, whether it's in your cell phone or it's in a small computer that's set up as a part of the LAN, the local area network in the spacecraft. And then the evidence-based algorithms for decision support and predictive analytics that are going to have to be kept up and revised regularly. So those are concepts. Let's get more into different types of technology now. As you know, many technologies are being designed for space, and this is just an example of PUMO, which is really a metabolic rate and analyzer, different gases, O2, CO2. One of my master's was in exercise physiology, so as you know, we took massive exercise human performance labs and had people doing VO2 max on big machines, and it's all been reduced down to this in terms of what they're looking at for metabolic rate for NASA. And then also ultrasound capabilities are highly important. It's our main imaging tool on board spacecraft right now. This is looking at imaging. There's ultrasound, there's retinal imaging. All of these technologies are being used in research ways right now in space. But each time you look at it, you start thinking, okay, can we miniaturize that? Can we decrease the amount of power? Can we get rapid feedback on the analysis side of it? This is an example of the astronaut doing it on himself, but previously, and still for some procedures, it requires 2 or 3 astronauts, which of course you can't afford if you only have a 3 astronaut mission. So the more we can get them self-administered, the better as well. And all of these continuous monitoring capabilities need to consider the spacecraft, but also keeping track of that astronaut when they're outside the spacecraft in an EVA or when they're in a planetary surface experience. And this is the new Artemis mission suit that was released at the end of last year. All of these areas are highly important to have very good surveillance of the astronaut, and each of their environments are different. So we've got to be able to have what I call concentric lands, land being the local area network, starting with the land in the spacecraft that expands out to include the astronaut in the EVA. So that land is the next circle. And then the next circle would be including the planetary surface information. And obviously the greatest land would be, it's not even local, it loops back down to mission control. So this idea of concentric circles of these assessment of these continuums. And again, striving to make all of this as non-intrusive as possible. So we're tracking the activities, tracking the information, but in the context of the astronaut living and doing and performing their mission tasks, where they're monitored every 5 minutes for what tasks they're doing, but in their activities of daily living as well, even eating and sleeping and voiding. And integrating this and leveraging augmented intelligence or AI in order to add information back. But again, going back to that value greater than nuisance. So how much of this can we do with ambient sensing, including what can we do about sensing how they use the keyboard, or are they changing the font? That might be a signal that they're starting to experience visual acuity problems, and their reaction time on certain tasks that they're required to do. All of that is information that needs to be fed into this. So sometimes we look way out in the future, and this is an example of person generated plus environmental generated plus power considerations. All of these are important. This is a bit of a futuristic slide, but a really nice article here that I wanted to point out. And even looking at sensors from different capabilities, some sensors that we implant will use local ionic changes to drive and power them. Some on the surface will use motion, and flexing of the motion actually stimulates a battery that helps power the sensor as they're gathering information. Or fabrics themselves that are both energy producing, but also are sensing. And so this is a very exciting time because all of these technologies continue to evolve. What we do have access to right now, though, is a lot of technology we're not using. So these wearable technologies, which many of you I'm sure have right now, they do give us valuable information. The caveat is many of them, they're not forced to right now, but we're working with the FDA on this. Many of them are not well validated, and they're not very stable. So across time, they drift. So we validate a lot of them. This is our Human Performance Center at UCSF, and we validate a lot of technologies. That's wonderful, but they do drift over time. But what information can we get from them that would be useful? How do we count on the information we're getting from them? And another thing to point out is that the FDA just started a Center for Digital Medicine, a center of excellence, and that's very exciting. That just got announced a month ago. So they're working towards creating standards for these things that will allow us to rely on that information. We also have a tremendous amount of remote medical grade devices now that are FDA approved, data we can rely on. These aren't all, not every picture up here is an FDA approved device, but as you know, we've got off-the-shelf devices. We've got scales and we've got O2 sat monitors and blood pressure cuffs that have Bluetooth enabling capabilities that are allowing us to start integrating these into clinical care of patients in their own home. We've got multi-parametric sensing patches we're using, smart stethoscopes. We've got image capability, so we can review images on our phones now. We can actually administer ultrasound and see it on the phone at the same time. This is the Butterfly IQ, which has generated a lot of interest. Some medical students are actually purchasing this. Some were given it as gifts for medical school. It's a good technology to get familiar with. It's got a long ways to go in terms of being, shall I say, valid in the hands of every user, but they're trying to build in AI that even tells you whether you're acquiring the signal correctly, not just interpreting the signal. And then of course, you know about continuous glucose monitors. They've been around for a very long time. Now they're integrating with AI and giving actionable feedback to the user. They're giving actionable feedback to the pump, and they're giving actual feedback to the medical facility and caregiver. This is a really exciting sticker that's come out recently. Again, no conflict of interest, but BioIntelliSense. This is a bio button. They've miniaturized it to a bio sticker. This is FDA approved for certain components, and that's what makes it really exciting. But it measures temperature. If you move the device, it's skin temperature, but they've got an algorithm that converts to core. If you put it near the axilla, you're going to get core temperature. But it also gives resting heart rate, resting respiratory rate, which is now found to be more sensitive an indicator of respiratory distress than O2 sat. The sat seems to drop later than the respiratory rate increases. All kinds of motion and position sensing, sleep detection, but coughing, sneezing, and vomiting frequency, these are indicators we don't have otherwise. So this has become a very valuable tool, especially in monitoring people for infectious disease such as COVID. But you can imagine the other questions you could ask with these disparate data streams integrated for you. This is a really interesting tool for looking at mobile metabolic rate. And I showed you the one, the Puma, that NASA's developed. And look at how this is getting downsized now. So here's a device on the right that people are using to look at what's their metabolic rate. Their resting metabolic rate is a function of their nutrition, their activity, their sleep, and guiding people as to perhaps what they might want to be burning instead if they want to lose weight or have more energy. This system, I don't know where it stands in terms of regulatory. This system is early in development, still breezing, but has gone through a highly evidence-based development path. So we're quite excited about this, measuring O2 and CO2 for metabolic rate, but also perhaps for some other parameters around concerns in the spacecraft environment. So these are examples of technologies we're looking at for metabolic rate. There are also going to be remote lab testing. We've got some up there already, but we're looking at how can we downsize what's there and also add a wider spectrum of testing capability, because all the reagents are susceptible to radiation, but they also have certain shelf lives and you can only take so many. So this is an example of an implantable sensor for lab continuous monitoring of certain components. Their chart is expanding, but initially they were looking at glucose and pH, et cetera. There are also circuits that are now printable, so could be printed in space. Some are being printed on chips for lab analysis. Some are actually now being printed on the skin for motion analysis. And again, back to the imaging capabilities, of which we mostly have ultrasound right now, but we are investigating a couple of companies that are miniaturizing MRI. It's not small enough yet, but also imaging such as X-ray that we haven't had access to in space. So some exciting technologies in that direction. And again, they need to be integrated into the suite, the health sensing matrix. This is an example of an optical sensing capability that's being developed. This is another TRISH project, the Astro 3DO, just using off-the-shelf 3D cameras, but highly developed algorithms validated against DEXA to be able to determine muscle compartment changes by compartment, lean body mass, overall and by compartment, and also looking at bone changes. And this is incredibly exciting. And ultimately, we'll be looking at fluid shifts with this. But this is a capability, I knew the researcher, I knew of his work for terrestrial care, and I said, we need this capability in space because we need in-mission tools for this. We have no good in-mission tools to assess bone and muscle loss and fluid shifts. We aren't quantifying them well. We have very crude tools, but you could imagine if we could do this, maybe combining with the metabolic rate assessments, we could give precision exercise prescriptions and precision and individualized nutrition and hydration prescriptions that could be flexible and change over time. So putting all of these things together, importantly, we're looking at how can we get to decision support, whether it's clinical or preclinical, ideally, and how can we get to risk prediction. This is an example of, there are 650 companies right now looking at clinical decision support tools in healthcare. And it's an exciting time. It's absolutely exploding. And on the risk prediction side, this is a really interesting company called Fatigue Science, and they're actually able to incorporate components of rest and recovery, including stages of sleep, duration of sleep, but also resting heart rate, resting metabolic rate, resting respiratory rate, integrating different streams and doing prediction of whether a person's going to have an acute episode of fatigue, maybe even a sleep, a nod, they call it, where you actually fall asleep, and whether 2 weeks from now, you're going to have a fatigue episode. So this is highly leveraged right now in high risk industries, including flight and also the military and mining, et cetera, so that they can allocate resources, including personnel, appropriately, but also help do interventions for people when they see that they're falling into patterns that are predictive of fatigue. And also, it's not far-fetched that we would be including genomic information in our precision space health continuum. This is Charles Hsu, a researcher at UCSF, and he sent one of the first genomic projects up to space, which Kate Rubins, we all know, who's back up there, did the first genomic analysis in space. So integrating the genomic information into all of this, not just pre-mission, where we need that information, but also in mission, where the microbiome is changing and we're exchanging microbiomes with each other, and viral reactivation is a concern, and looking at the ways that genomics may play a role in mission. Also, how do we have sustainable resources? People have heard of made in space 3D capabilities. We're going to need to do that, not just to replace tools or parts, but also possibly to create medical procedure instruments if we needed to do medical procedures that were somewhat invasive. And finally, compounding and printing medications. This is a very exciting field that 3D printing is playing a role in. NASA is working on all of this. And what's exciting is the opportunity to intersect with them on this through the medical data architecture team. They're working on these concepts of integrating data and then creating information out of them in closed loop processes to get to this precision and personalized health. And ultimately, instead of looking at the panome, as I call it, in separate categories, so the genome, the phenome, the microbiome, what I now call the phonome, integrating all of those data streams into a way that gets us to this personalized health continuum. And when we add into that historical data, lessons from prior astronauts, the longitudinal study of astronaut health, and integrate that with the individual parameters of the astronaut that we know, then what we can do is get to something that we call not the panome, not in the individual ome, but the person's ome, or what I would call here, because this is Peggy Whitson, most of you recognized her as one of the women with the longest number of hours in space. But ultimately, we may come up with the pegome. So each person will have their own integrated suite of information. So I'd like to just say I find it a great privilege to work at TRISH, and I'd love for you to know more about them. Please log in. They have fantastic educational information and opportunities to apply for programs. Go in, you would type in this website, and as you scroll down, look for the Red Risk School. There are a number of videos that you can access through there that are highly informational. And then always we're posting opportunities. Right now, we currently have an opportunity for a space health postdoc fellowship. And also there's a solicitation out, a large scale solicitation looking at metabolism and homeostasis in space. So please take advantage of the TRISH opportunity. We have a wide open door. We are constantly interested in building community. In my own work at UCSF, anyone who's interested in this idea of sourcing innovative solutions for space, please contact me. It's my ongoing work. I'm also building out the health sense matrix and a proof of concept around that, and have an opportunity for someone who'd like to do a fellowship. We have an opportunity with the UC Space Health Fellowship as well. Thank you very much for this opportunity.
Thank you so much. We have 4 questions queued up already, not counting the questions that WAM leadership has, which are many. And I know that we're getting close to the hour. If anyone needs to leave, of course you can. Please stay if you'd like. Members, please stay if you'd like. We're going to have a conversation after Dr. Sawyer departs about representation and some use of terminology. We love your feedback. But in the meanwhile, the first question comes from Dr. Posselt. Would you like to unmute yourself and ask your question, Bonnie?
Hi, Aenor. Lovely to see you. Thank you so much for an awesome
Hi.
presentation. I know it's been a long time. It was 2 years ago that we were in, or a year ago that we were in Edinburgh together. Absolutely fascinating presentation that all this new exciting kit is out there. My question is, with the massive amounts of data that you're going to be collecting, vast, how do you go about interpreting it? Is there a risk of there being too much noise or taking too much, putting too much emphasis on an incidental finding?
It's a really good question, aside from errors that can occur that need to be filtered out. But it's a great question. But I always say, start with the use case, start with a question. And this is going to be a slow process to get to this overall continuum that monitors the multi-parametric, the multiple changes happening. But I'm really driven by the so what factor. So starting with the question first. Even so that tells me exactly what data sets I'm going to need to answer hydration or fatigue or nutrition or even respiratory distress. So picking those things first. Pick one of those and work on that and work it all the way around in the end-to-end journey. And then, yes, there will be questions of what's noise and what's not. So trying to find those ranges, and this is a big part of clinical decision support. What's in range, what's out of range, and what's a critical range? And you know all this from medicine. We have to do this constantly with our lab results and with any parameter we're measuring. We've got to create ranges. And a lot of that starts from big population data sets, and then we've got to keep refining it down as we gather more data on each astronaut and in the space environment. So it's complicated. You're absolutely right. But if we don't start with specific use cases and really do the end-to-end journey, we're not going to be able to get at that. Some of the problems of artifact have been solved in other ways. I mean, in fact, the EKGs we get, it's nowhere near what the raw data looks like. There are a lot of smoothing algorithms that come into play. But you don't want to lose critical data, but you don't want to have artifact data or meaningless data. So that's going to be a part of the whole exercise.
Yeah, it's just like when you're trying to discharge someone who's got a broken foot, but for some reason, someone took a troponin and it's raised and you're... Anyway, thank you very much.
And it is absolutely to the point of metadata, like what data matters. Yeah.
Mm-hmm.
Cool. That was a great talk. I'm just going to read a question from Dr. Lehan Kao because she can't unmute herself. So this is kind of similar to the question that was just asked, but with the reliance on individual baseline data, perhaps extrapolated via data from past astronauts, how can we overcome known gaps due to limited diversity of astronaut teams? So even on Earth, this seems to be a problem, like caring for diverse populations. But much of research data comes from less diverse subjects. I was definitely a research subject in undergrad a lot, and I know that half of the research participants were undergrads who fit my demographic more or less.
Great. Where's Dr. Cowell from? It's okay, but I'd love to know where people are from. So let me just say that.
State University.
Oh, fantastic. Thank you.
I think she just isn't herself.
So to that question, if we don't start, we'll never know more. We'll never close any gaps. And so there are many reasons why this is going to be hard. And what we have to do is make sure that we're very honest about not extracting too much meaning. Some of this, like I said, with the MS Bioscreen is purely observational right now. And before we can get to predictive and prescriptive, we've got to gather a lot of data. And so right now, we're just not collecting very much in a systematic way. And so I think the main answer to that is be careful about the assumptions you draw from the data you have initially, and make sure that you're gathering the information so you can start answering these questions and filling these gaps. And yes, across a diverse population, that is absolutely essential. And there will still be some broad assumptions that we have to extrapolate across the astronauts. And we've been doing that for years, and we've been fairly successful. We've had very few catastrophes. But we think on the longer duration mission, the risks for those things could go up. And if it's not a catastrophic event, something that would have a long-term health consequence, we also want to prevent, or decrease a performance, which would then threaten the mission. So what we have to do, though, is we have to start with using the broad knowledge base that we have and relying on it. Then we get narrower and narrower and narrower by collecting more information on more individuals. But be really careful about what assumptions you draw out of the information you get.
Yeah, that sounds great. And I hope that answered for Dr. Cow. And I think next we have a question from Dr. Rosal. So if you want to unmute yourself, please go for it.
Sure, not a doctor yet, just a medical student. Hey, thanks for this great and super interesting talk. I'm Sophie, I'm from Germany, but I actually do work on a paper with TRISH with Emmanuel.
Oh, great.
Yeah, but I really like the idea of being a surgeon and in being in health tech. So I have more of a personal question. Where did you get your background in tech health, and did you feel, or would you say it would be hard getting started in tech health without a degree in, say, engineering, physics, or computer science?
So I evolved into it. I started as a physical therapist, then an exercise physiologist, then I became an orthopedic surgeon. But across all of that, I wanted to empower people to take better care of themselves, which meant I had to understand more of what they were experiencing in their own environments and give them tools to help themselves in those environments. So it's really been driven across my whole career. And the more I got into technology, device, but also digital health, the more I understood the power of it to enable people to do that. And so it's a continuum of very, very early on home care and physical therapy. And it's continued across my whole career. What I will say is it's challenging to be a clinician innovator. So I teach a health tech elective at UCSF, and I'm constantly trying to support this pathway to become a clinician innovator, a research innovator, whatever, because there's no roadmap for it. And there's actually a lot of pushback, and it's not incentivized in your metric system. So if you have questions about that, I'd be happy to help. I'm working on a national committee to build that into academic metrics, et cetera. But the clinician innovator role, I think, is critical. Frontline innovators are critical to transforming, whether it's healthcare or any industry. They're just, it's so important. So I'm happy to talk to you about that. The answer is I evolved into it, and I kept seeking and following paths of things that were of interest and that I thought would have meaning, not just in that unique setting. There aren't very many ocean rowers, fewer than there are astronauts, but truly all of that information transfers back to any low resource setting I'm trying to provide care in. So that's how I've looked at it, but I'm happy to talk further offline if you wish.
I would love to. Yeah, it sounds great, especially the electives that you're teaching. That's very cool.
I'd love to interject with a quick follow-up question to that. So how do you go about, you presented a lot of really interesting examples of monitoring devices or systems that you found. How do you find them? Do you go to conference, like where do you look for them? Do you really solicit them, or do you knock on doors?
Yes, well, it's so interesting because there are so many venues for this now. There are many, many online sites. Some of them are subscription because they're meant for venture capitalists, where they're landscaping technologies in different categories. A lot of them come to me now. Like I do speak to 6 to 10 startups a week because my work at UCSF for 12 years has been in that role. Started the Center for Digital Health Innovation, and I'm on the procurement committee and the IT Governance Committee. So I get brought these things, but I do a lot of advising outside. Really, much of it's pro bono, so I can have access to the landscapes at innovation centers with companies that I think are doing something that's evidence-based and needs some frontline information, and also with other universities. So it's a matter how that's grown over time as well. But you don't have to be in a position where it's coming to you. Mine is push and pull. A lot is coming into me, but I am constantly surveying. And the way I do that is through conferences. Oftentimes a conference will also have some sort of a showcase, and you can scroll through the exhibitor section, and then you can do a deeper dive. It is time consuming. If you just look at the reports, CSB has a report. I mean, every big advising company now has a digital health report or more. But I work with groups like FDA, ONC, that's the Office of the National Coordinator, which has a lot of the digital health information. Those are great documents they put out, by the way, if you want to learn more about it. But what I do is I look at the government sites and I stay active. I play volunteer roles so that I can stay up to speed on things. And then the other is in the conferences, I look through the exhibitor section, and that's on every digital conference advertisement. And I have other sources that come through organizations that I'm involved in, the boards that I'm on that were mentioned earlier. So you don't have to have 20 years in the field to get access to the information. That's the beauty of the internet and our ability to look for things. I would say look for organizations that are focused on evidence. So Node Health is a good organization. It's evidence-based. It's nonprofit. HIMSS is a phenomenal organization that's a large nonprofit global health information community, and that's another very good resource. Look for their conferences, look for their startup showcases. Startup Health is a great innovation incubator, and they also have, every incubator has its portfolio, but so that's another way to look at it. But then you also want to look at the big organizations. I don't mean to have overlooked any, so I'm not listing just preferences, but ones that I do use a lot.
No, that's really good to know. I've been involved in a couple innovation challenges here at my university. So,
oh, good. And the main thing to keep in mind is you can get very excited about one solution, but in each category, there should be mini solutions that are being built up, and you need to learn how to do due diligence. Don't fall in love with the one. Some of them are very seductive. And so you've got to set some criteria of what would mean success in the category you're looking in. And then look across, try not to fall in love with one at a time.
Cool, thank you.
All right, I know I've gone past, sorry.
No, we're just chatting because we love being here. And one of the brilliant things Dr. Sawyer has done is start this annual conference for space health innovation.
Yes.
And everyone has to come to her.
Well, please do note. Thank you. You're so kind to bring it up. We had to cancel this year, but it's the Space Health Innovation Conference. It's an intersection of NASA and space health experts with the health tech community, with the healthcare community. So it's an intersection, it's a mashup of those worlds. And we have it planned coming up in September of 21, but the date's not set. We're hoping it'll be hybrid, so part virtual, part in person, but we'll see where we are at that point.
Well, we've got another question coming up. And after that, anyone who wants to stay and chat, you'd be more than welcome to. We'll just stop the recording.
I think there's a question from Lynn Stanwick was next after Sophie's. So if you want to unmute yourself, go for it.
Hi, thanks for the talk. It was great. My question was, you mentioned things about like genomes playing a big role. Has anyone looked into gene therapy, and is that going to potentially play a role, or is that something that's going to be too unpredictable?
Well, right now it's even way far off in healthcare, although we're seeing some stunning examples now that CRISPR's come into play, where we can actually snip out certain things and insert others. That is unbelievably exciting. So gene therapy, I think in terms of space, is fairly far out, but something a little closer in. But nothing's off the table for TRISH. I mean, that is our role, is to really look at way out there things. So yes, ultimately, if we're talking about long-term missions or eventually existing on other planets, that will have to be a part of it. But the main thing I want to think about, because you will have damage from radiation, and can we correct for that over time? the other thing I would say is what's closer in my mind is stem cell and the ability to bank stem cells and to do repair. We're using stem cell repair, mesenchymal stem cells in MS musculoskeletal things right now. So to me, that's not that far out there. We also talk about, obviously, creating a human blood bank, knowing who's got what blood type, et cetera. But the stem cell one, I think, is really interesting. There's a lot of work to be done on it, but I think that does have a lot of potential. Before we ever got to the idea of doing gene therapy in space, it sounds fantastic, but it's again goes back to the tenets of space. Is it space feasible? Would we ever be able to have the machinery and all the capabilities to make that a reality? I don't know, but I never say never. I've seen things evolve so rapidly from impossible to, wow, we're ready to try that. And so I think it's cool to keep asking those super edgy questions.
Thank you.
All right, I want you to have time for your meeting. So everybody stay safe and celebrate in whatever way is safe, in whatever angle you want to, but it's very, very important that we all work together across whatever our disciplines are, or even our political biases are, that we work together to continue to make life and optimization of health and medical management for everyone a reality. So thank you so much for this opportunity.
Thank you.